Another type of indeterminate form that we want to explore is the type 0 times infinity. Now this is going to be an indeterminate product. So we'll see limits of the form f of x times g of x, where one of the functions will go to 0 and one of them will go to infinity. Some form of infinity. And the reason why we'll be able to evaluate these using L'Hopital's rule is because these can always be manipulated into a form that's either 0 over 0 form or infinity over infinity form. So if, for instance, if we have the limit as x approaches a of f of x times g of x is of the type 0 times infinity, then we can manipulate it a little bit, because I can write, for instance, I can take this one here that goes to infinity. If I flip it over and put it in the denominator, then you got something 1 over infinity that goes to 0. So this will then be in the 0 over 0 form. So we can do a little bit of manipulating, right, because this will equal to something that can be written in the 0 over 0, or we could also do the infinity over infinity form as well. So let's look at how that works. Say, for instance, I want to find the limit as x approaches 0 from the right of x times ln x. So just to remind you, ln x looks like this, right, the graph of ln x. So it goes to negative infinity as x approaches 0 from the right. It's got that vertical asymptote. So this will be in that form 0 times infinity here. That's negative infinity. So what I can easily do is just move this x to the denominator by flipping it over. So I got ln x on the top and then 1 over x on the bottom. Now we see that it's still going to negative infinity in the top, and then 1 over x as x approaches 0 from the right will go to positive infinity. So now it's in that infinity over infinity form. So now it's in a form where we can use L'Hopital's rule. So let's apply it to this form here and see what we get. So taking the derivative of ln x, we get 1 over x. And then taking the derivative of 1 over x, which is like negative x to the negative 1, so that's negative x to the negative 2, or negative 1 over x squared. And then simplifying this a little bit, I'll get, let's see, negative x squared over x, which is just negative x. So it'll be 0. Okay, so thereby rewriting this in the infinity over infinity form, we got it into a form where we can apply L'Hopital's rule. Let's think about how we can use L'Hopital's rule to help us sketch the graph of f of x equals x e to the x. So as it is, we can see that as x goes to infinity, this will certainly go to infinity, right? So taking the limit as x goes to infinity of this, you got a product of something that goes to infinity times something else that goes to infinity. So it'll blow up as it goes to the right. So the question is, what happens as x goes to negative infinity? And in this case, well, we can think of this as now an indeterminate form of the type 0 times infinity, because you got here this would go to negative infinity, right? E to the x would go to 0. So similar to how we did it before, we'll rewrite it into a form where we can use L'Hopital's rule. So I'll write e to the x in well, actually here it doesn't really matter which one I can bring to the bottom. I can leave the x in the top and bring e to the x to the bottom, or I could do the other way around. Let's see what happens if I do it this way, if I take x over e to the negative x. So I leave it x in the top, but then I'm going to bring this e to the x term to the bottom as e to the negative x. So now we see it's in this negative infinity over infinity form. So let's apply L'Hopital's rule. We got something where I take the derivative of x in the numerator as 1, and then the derivative of x e to the or e to the negative x will be negative e to the negative x. Okay, so here we got the limit as x approaches negative infinity of negative e to the x, which now as x goes to negative infinity, this will be 0. So that shows us that as the graph goes to the right, it'll tend towards the x-axis. So we know as it goes to the as it goes to the left, it'll tend towards the x-axis. As it goes to the right, it'll blow up. So we kind of have an idea of how it's behaving at the ends. But one more thing we can do to analyze it is to figure out what it does, where it's increasing and where it's decreasing. So I'm going to quickly just take a derivative. So doing a little product rule here, we get e to the x plus x e to the x. You can factor out an e to the x. We see this is equal to 0 when e to the x will never equal to 0. So when 1 plus x is equal to 0, we get x equals negative 1 is our critical point. So at negative 1 is where it may reach a max or a min. Let's just quickly check whether it's a max or a min here. So if I choose a value of x that's less than negative 1, I think this will be a negative value. And if I choose a value of x that's greater than negative 1, this will be a positive value. So you see it's decreasing and then increasing. So it looks like we're going to have a min, local min at x equals 1. So I think our graph would cross through 0, 0, hit a local min there at negative 1, and then it'll tend towards the x-axis as it goes to the left, and then it'll keep going to infinity as it goes to the right. Let's look at another type of indeterminate form where we have the form infinity minus infinity. So this will be an indeterminate difference. And what is this type? Well, this is when we have a limit of the form f of x minus g of x, where both f and g go to infinity. Okay. And so what we'll be looking out for here are more algebraic maneuvers that we can use to manipulate it into a form where it's either 0 over 0 or infinity over infinity form. Take for instance here we've got the limit as x approaches pi over 2 from the left of secant x minus tangent x. We can easily see that both these graphs are going to have a vertical asymptote at pi over 2. If you remember, the graph of tangent will look something like this, where at pi over 2, okay, it's got that vertical asymptote. Secant will similarly have a vertical asymptote at pi over 2. So the graph of secant looks a little different. It looks more like this. At pi over 2, it'll have a vertical asymptote as well. So it is in that infinity minus infinity form, right? And what can we do here? Well, one thing we can do is just try and rewrite this in a different form. So secant is 1 over cosine. Tangent is sine over cosine. So when I combine these together, we have 1 minus sine x over cosine x. So looking at it now, it appears that we have something in a different form. Because now we have in the numerator 1 minus sine x. We know sine of pi over 2 is 1, so this will approach 1 minus 1 equals 0 in the numerator. And cosine of pi over 2 is 0, so this will be 0 in the denominator. So we got the 0 over 0 form. So now it's in a form where we can apply L'Hopital's rule. And applying the rule here. So the derivative of 1 minus sine x in the numerator will give me negative cosine x. And the derivative of cosine x gives me negative sine x. And as x approaches pi over 2, now it looks like we'll have 0 over 1. So it'll be 0.